What science is and how and why it works.
Let me start by reminding you all, as you know, that one of the great accomplishments of 20th century physics, perhaps culminating 2,000 years of studying the structure of matter, was the construction of what is called the Standard Model, which is represented here by a list of the elementary particles, the elementary constituents of matter, quarks and leptons, 3 families, altogether 6 times 3 colors, 18 quarks, and electrons and neutrinos, and 2 copies of electron-neutrino families that don't feel the strong force. In addition to enumerating, discovering, and measuring the properties of the elementary constituents of matter, more importantly, the Standard Model is a theory of the 3 forces that act within the atom, within the nucleus. All of these forces are of the same nature. They are all based on beautiful local symmetries of nature. Electromagnetism is the first such theory developed by Maxwell, where we have 1 electric charge. But remarkably, the 2 forces that act within the nucleus are of a similar nature, except that in the case of the weak nuclear force responsible for radioactivity, there are 2 charges. And in the case of the strong nuclear force that holds the quarks together inside nucleons, there are 3 charges. Together with a Higgs sector that is needed to understand the properties of the weak force, we have the complete Standard Model, by now, all of whose properties have been confirmed in literally hundreds of precision experiments. This is really a fantastic achievement of mankind. And it is, although it's called the Standard Model, it should really be called the Standard Theory, because it is so unbelievably successful, and you can put the mathematical formalism on 1 t-shirt. When physicists say that a theory, and this is really a theory, a comprehensive theory of matter and force, a theory is beautiful. What do they mean? To the uneducated in the mathematical physics, this hardly might seem beautiful. But to us, it is gorgeous. And part of what we mean by beautiful is that it is so powerful. In principle, we believe that this theory could explain, if we were to work hard enough, just about every measurement that we perform in our laboratories today. Of course, we can't, except in special circumstances, calculate things precisely, but we believe the theory has this power, and it's based on simple and elegant principles. It is certainly beautiful. The part that I will be discussing is the theory of the strong interactions, which is really described by this 1 term here. Much of the complications and ignorance that remains in the Standard Model has to do with the other parts, those that describe the electroweak interactions. So this is the standard theory, and it developed from the Greeks, Democritus, over thousands of years, but especially in the 20th century with the growth of accelerator physics, and culminated in the latter part of the 20th century. But the road was not simple. And in particular, in the case of the strong nuclear force, there were extreme difficulties in understanding and finding the explanation of, or even identifying what nuclei are made out of. The reason, in retrospect, is obvious. The charges of these forces, the analog of the electric charge, which we call now color, the color charge, red, white, blue, or red, white, green, depending on your country, and the gluons, the particles that are the glue of nuclei that hold the quarks together and also carry this color charge, are completely hidden inside the nuclei and not visible to the outside. To an outside observer, a proton or a neutron or a nucleus has zero charge. That made it very difficult to identify the constituents of the nucleon, of the proton, and it made it even harder to identify the nature of the force that holds the quarks together. And finally, when people smashed particles together, as you will do in Nika in the collider, what came out were particles very similar to protons and neutrons, pions, strange particles, but never any quarks. So although it appeared already from the early 60s that the systematics and some of the symmetry properties of the hadrons, the strongly interacting particles that were produced in these collisions, could be understood if you assumed mathematically that nucleons were made of quarks, fractionally electrically charged hypothetical particles. No one had ever seen a quark. No matter how hard you smashed nucleons together, there were no quarks coming out. So nobody truly believed in the existence of quarks until the late 60s, 1960s. From my point of view, the experiment that really convinced me and others and of the existence of quarks and turned out to be the key to understanding the strong force, which was described by a theory, what we call a gauge theory, a theory based on local symmetries of nature, very similar to Maxwell's electrodynamics, already had existed since the 1950s. But attempts to apply it to the nuclear forces, the weak and strong, failed because of lack of understanding of how that force could be hidden. The experiment that changed the scene was the so-called deep inelastic scattering experiment at SLAC. This was an experiment that is very similar in nature to Rutherford's famous experiment done in 1911-12, when Rutherford smashed alpha particles from radioactive decay onto gold nuclei, the same gold nuclei that, well, gold atoms, the same gold atoms that you are going to strip and collide at Nika, in order to study the properties of atoms, the structure of atoms, and he discovered the nucleus of atoms. He discovered that inside the atom, there's a very small core which contains most of the mass and all the positive electric charge of the atom. That was the beginning of nuclear physics. That was the beginning of particle physics. Rutherford taught us that to study the properties of matter at very short distances, what you do is you smash one kind of matter, another kind of matter, and you look at what comes out. Rutherford used this method to discover the nucleus of atoms, leading within 2 years to the Bohr model and a theory of atoms, and then to quantum mechanics. This experiment did the same thing. It used photons, a quanta of light, scattering off protons to probe the structure of the proton. And it discovered that the proton looked as if it were made of freely moving point-like particles which obeyed certain relations that indicated that they perhaps were the sought-after quarks. You could see inside the proton in these experiments, and in a sense, you could see quarks moving freely around, fractionally charged quarks. This is a pivotal experiment which won the Nobel Prize for, quote-unquote, the discovery of quarks. Of course, quarks never got out. No one has ever seen a freely moving quark. But this experiment, much like Rutherford's experiment, allows you to see inside the atom, or in this case, inside the nucleus, inside the proton itself. But this is very strange. How can it be that quarks move freely around if you look at them over very short times, not far apart? And yet, if they're free, moving around freely, nothing holding them together, then you should be able to easily knock them out of the proton. Just like you knock electrons out of the atom and make them run in wires and do work. Why can't you knock the quarks out of the atom, out of the nucleus, and make them run in quark wires and make them do work? It'd be very interesting, but you can't. No one succeeded. So that was the puzzle that, in my case, motivated, drove me to work very hard to try to understand this freely moving behavior of quarks inside nucleons. How could you possibly explain it? Of electron-neutrino families that don't feel the strong force. In addition to enumerating, discovering, and measuring the properties of the elementary constituents of matter, more importantly, the Standard Model is a theory of the three forces that act within the atom, within the nucleus. All of these forces are of the same nature. They are all based on beautiful local symmetries of nature. Electromagnetism is the first such theory developed by Maxwell, where we have one electric charge. But remarkably, the two forces that act within the nucleus are of a similar nature, except that in the case of the weak nuclear force responsible for radioactivity, there are two charges. And in the case of the strong nuclear force that holds the quarks together inside nucleons, there are three charges. Together with a Higgs sector that is needed to understand the properties of the weak force, we have the complete what is called the Standard Model, which is represented here by a list of the elementary particles, the elementary constituents of matter, quarks and leptons, 3 families, altogether 6 times 3 colors, 18 quarks, and electrons and neutrinos, and 2 colors.
What science is and how and why it works.
Let me start by reminding you all, as you know, that one of the great accomplishments of 20th century physics, perhaps culminating 2,000 years of studying the structure of matter, was the construction of